your. Yeah. Yeah. Ooh, it's early. Excuse me. Okay, we are recording. All right. Let me put this here. All right. We'll get started in about 2 minutes. We're just going to go over the formative. Just let a few more people get on. It's like it's a packed house today. This over here. And if you have any questions while we're going through this, just post them in the chat window. Oh, my family, every time we have class, my family goes out for a walk because there's no way I could have a class and have my family in the house. It would just be too crazy. You'd have kids running around the background. Like every lecture of your life. And yeah, and my wife's not quiet either. She's pretty loud. So, you know how it is. So they have to leave the house so that I can do this. So I hope everybody has coffee. All right. So the formative is pretty short. Some of it's rather maybe a little tricky, but we'll do our best to go through it and unpack it and just sort of like enlighten if you're still confused. Actually, I like this arrangement better. Perfect. All right. All right, so the formative is not something that you should be stressed out about. It's just data for your teachers. It's data for us. It will not be graded as an assessment. It will just be graded as classwork. But it only is counted if it helps your grade and does not hurt your grade. So there's a lot of if-then statements embedded in that. And if you have trouble understanding kind of what's going on and how all of this is being factored into your grade, please feel free to schedule a meeting with me, 10, 15-minute meeting with me, and then we can just sort of like unpack what's going on and see how it's impacting you. I met with a few students this week, and it was kind of nice just to talk to people and kind of see where everyone's at and how they're doing. So I'm available, and my office hours are posted on the Google Classroom, and you can schedule a time slot with me using Calendly. All right, let's go ahead and get started. It's 8:03. And so, again, this is just a practice formative. This, for the week, will just be counted as a classwork grade. If you attempted it, that's it. Another thing I want to say is that your grades on Aspen will more or less be your grades for term 3. If you're looking to change that in any significant way, please reach out to me and we can have a meeting and kind of discuss that further. From my understanding, there will be no term 4. So term 3 is the final grade. And from Dr. Wisdom's, we met with her on Monday, the science team, and she said that we will not be having a final exam. That was her understanding. But she said, things are changing sometimes. Things have been changing. But she said she doesn't expect a final exam. Okay, so let's call this, the questions aren't numbered, but let's call this number 1. Which of the options above, they're actually below, represents a skydiver falling from the sky with a constant velocity? If your velocity is constant, forces are balanced. So if you're falling from the sky, you're falling downward, all right? So you're going down, and there's an equal but opposite force, the friction that's acting against the direction of your fall. So if you're falling down, air resistance is opposing your fall, and so you would have a free body diagram that looks like B. I'm recording this and I'll post it, and I'm getting better at posting these things. I realize that I have to use my work YouTube account to post things, not my private YouTube account, because I have unlimited storage on BPS's YouTube account, so I can post really long videos. Which of the options below represents a student accelerating in a 100-meter race to the left? If you're accelerating to the left, that means you have to have a force arrow or a net force to the left, all right? The only free body diagrams where you have a net force to the left are D and E. I did not say ignore friction. So if you're moving in a direction, you always have friction that's acting against your motion. So if you're moving to the left, then you have some friction that's opposing you to the right. So you're accelerating to the left, that means you have force to the left, and then you have a little bit of friction. That's why if you've ever seen Sprinter spikes, really cool shoes to look at and even try on. But Sprinter spikes, there's these really lightweight shoes that just wrap around your feet. They're just so snug. And on the bottom, they have these metal spikes, these really sharp spikes that dig into the rubber track to provide a lot of friction when you're sprinting. Really cool shoes. Let's see here. And so the answer here is E, because you have a net force to the left, and so therefore you're accelerating to the left. A student pushes a 12-Newton book to the right with a force of 10 newtons. All right. The 12 newtons here refers to the weight of the book, right? And that's your weight, your force of gravity, weight, same thing. But this is resting on a surface. So you have a normal force that opposes the force of gravity, that weight, all right, to keep it on the surface. Let's see here. And it says here we're pushing to the right with 10 newtons, and then there's a force of friction. It's about 3 newtons. And so what is the magnitude of net force? Well, you just subtract all the forces that are in opposition. So 12 minus 12, there's 0 net force up and down. 10 minus 3, there's 7 newtons that would be acting to the right. Okay, that one's pretty straightforward. If you have questions, just note them in the chat window and I'll get to them as they come up. So which of the following describes the difference between kinetic, all right, by now we should know kinetic means just motion, just anything that's moving, and static friction. Static things are not moving, all right. Let's see, if you are interested in becoming a civil engineer or an architect or a structural engineer, all, might I add, great jobs. They are some of the fastest growing jobs in this country, predicted over the next 10 years. And they make easily, you know, into 6 figures with some experience. You will have to take a class called statics. Why statics? Statics means not moving, right? When you design a building, you don't want that building in general to move, all right? So you need to study how forces are balanced in a structure so that it does not move, all right? The only exception to that is if you go to certain really tall skyscrapers. I went to Taipei, and I went up to the tallest structure in Taiwan called Taipei 101. And at the top of that structure is a huge mass. All right. The mass is bigger than our classroom. All right. It's a giant sphere. What it does is it locks in the top of that building so it doesn't sway in high winds, but the building below it does move a little bit back and forth in high winds. And that's to provide a little bit of give so that the structure isn't so rigid. And that can, if you have a really rigid structure, then you have a brittle structure. And then if that structure is brittle, it's more likely to break when high forces are applied instead of bending. But here, the difference between kinetic and static friction. And the answer is here. So one type of friction is motion. That's kinetic friction, is due to motion. and the other is for stationary objects, right? Static friction. So static friction is just the friction you need to overcome to get something to move, and kinetic friction is the friction that you have when you are moving. All right, it's been really difficult for us to get moving some days. That means we have a lot of static friction that we have to overcome. A person with a weight of 600 newtons is standing on a scale. What force is the scale exerting on the person? If you're sitting on or standing on a scale, all right, and you have 600 newtons that your force of gravity is, then that scale is also balanced, about providing a balanced force and pushing up with the exact same force of 600 newtons, all right? Let's see here. Chloe pushes this gets a little bit more complicated. This is the free body diagram one, where you're exerting a force at an angle. Two of the three physics classes did not go over angled forces, but they're not much more complicated to interpret than what we've done. Chloe pushes a 3.5 kilogram box up a wall with a diagonal force of 120 newtons, as shown. Let's see if I can zoom in. Nope. All right. Let's see here. Which of the following is the correct free body diagram for this situation? Now, let's see here. So there we go. Perfect. That's what I want to do. All right. This is the right free body diagram. Now, let's go back up. Here we have, what's the kid's name? Chloe. Chloe is pushing this box, and she's not pushing straight on this way. She's pushing up at an angle. If you take a book and you kind of push up at an angle, that book, you can cause it to slide upwards. It says here you cause the book to slide upwards. What the heck's going on here? Let's see here. There we go. All right. You can cause that book to slide upwards. A lot of forces involved here, and we did this demo in class. I think I took a book, I pushed it up against the wall, and I pushed the book against the wall, and the wall pushed the book back against my hand. The force of gravity is pulling the book down, but the friction between the book and the wall is holding it up, okay? So that's one case, right? Now we have here a completely different scenario, or somewhat different scenario, but our force diagram is going to be different. So here's where it gets a little bit challenging to interpret. We are pushing the book at an angle against the wall. We are angling how we apply that force. So this force applied is angled. This is true. Now, the book is being pushed against the wall. That means the wall's pushing back with a normal force, okay? Gravity on this planet, always down, right? So the force of gravity is always down. And now, because that book is sliding upwards, we have a force of gravity that is opposite of its motion, okay? So that's why we have all of these funky forces in the arrangements that they are in this diagram. It's a little bit complicated, and it took me a second to kind of process that, but this all makes sense. All right, let's see here. And if there are no questions, I'm just going to move on. So if you have a question, you can post it in the group chat. I'm recording this, and this will be available on the Google Classroom after the session. So Chloe pushes a 3.5 kilogram box up a wall with a diagonal 120 Newton force. So this is her diagonal force. And just like any triangle, you can break up that triangle into vertical and horizontal. You can make the diagonal into a vertical and a horizontal component using cosine, sine, and tangent, right? You can figure that out. We're causing this book to slide upwards. Which of the following correctly describes the magnitude of the friction? Now, hint, use the gravitational constant of 10 meters per second squared. Now, let's see here. Calculating the magnitude of friction. Now, we did go over this equation in class weeks ago. I can't even count how many weeks ago. I don't even know what day of the week it is, barely. I think it's Thursday. But the friction force is F. This is the friction force is equal to your coefficient of friction. That tells you how much friction there is, multiplied by your normal force. Now, if we go back to where we were, our normal force is the force of the wall pushing back on this book. Now, if this horizontal component is 72, that's how much force we're providing horizontally, going across horizontally to keep that book on the wall, stuck on the wall. All right. If we're pushing horizontally with 72 newtons, then the wall is pushing back with the same 72 newtons. And that force that the wall pushes back with, that is our normal force. If our normal force is 72 newtons, all right, so let's just write here our, well, F, so our force of friction equals our mu. So mu is the coefficient of friction times your normal force. All right, so our normal force equals 72 newtons. All right, let's see here, 72 newtons. Our coefficient of friction sliding, because this is moving up the wall, is 0.5. So mu, which is our coefficient of friction, is 0.5. Now our force of friction, mu times our normal force, so that's just 0.5 times 72. So we should get, what's that, 36 newtons. Yeah, 36 newtons. All right, here. All right, so Melissa pulls, if there are no questions on that, I'm just gonna move on. Melissa pulls on a 100 kilogram plastic box as shown with a 500 Newton horizontal force so that it slides across the ground at 2 meters per second for 20 meters. A lot of information here, but only some of it will be relevant. Identify how each of the following variables will change if she pours water on the surface. Okay, one, if you pour water on the surface, one, your force of gravity. Your force of gravity is constant. It's not going to change unless you change the mass, which the mass hasn't changed. It's still 100. Or you change gravity, and gravity is still, the acceleration due to gravity is still 10. So your force of gravity is not going to change. It's going to stay the same. The normal force from the ground. If your force of gravity doesn't change, which is the force pulling it down, then the normal force, which is the force that the table pushes up with, is also not going to change. All right. So your normal force of gravity, stay the same. Your force of friction. You are putting water on the surface. Generally, when you put water on a surface, things slide more easily across the surface. Okay. So therefore, if things are sliding more easily across the surface, your coefficient of friction, that mu, is going to decrease. If mu decreases, then your overall force of friction is going to decrease as well. And your coefficient of friction will also decrease. Right? So these two decrease. More water on the surface, then things are going to slide more readily. All right, no questions on that. I'm going to move on. Okay. Two forces, F1 and F2, are applied to a block on a frictionless horizontal surface as shown. The block has an acceleration of 2 meters per second squared, that should be. What is the mass of the block? All right, so here we have two forces. They are unbalanced, 12 to the left, 2 to the right. The 12, let me just put that here. So F1 F2 equals 2 newtons. So, and the block is accelerating at 2 meters per second squared. All right, 2 meters per second squared. What is the mass of the block? So let's find the net force first. So the net force, okay, it's just going to be F1 minus F2. That's 12 minus 2. So your net force is 10 newtons. All right. We know that force equals mass times acceleration. All right. So we have net force of 10 newtons. We want to know the mass, and our acceleration is 2. So we're going to solve for the mass. So your mass is just 5 kilos. All right, so your mass is 5 kilograms. That's how we get that. And let's go down here. All right. In which direction will this object move? Well, we have a net force of 10, and that is to the left. Greater force being applied to the left. Oh, wait a second. Why did it say which direction? Let's see here. No, that's not true. It should be to the left here. Answer key is wrong. I'll adjust that. All right. Let's see. I'll have to let the other teacher that made this know. So let me note that. Hold on. All right. Email her. All right, Kevin. So again, this one, you have a net force to the left. So this should be moving to the left. All right. Kevin pushes a 50 kilogram box with a horizontal force of 60 newtons. What is the normal force? Your normal force is basically your force of gravity. So if you know that your force of gravity is just, let me write this down just in case you forgot the equation. Force of gravity is equal to mass times g. In this case, the mass is 50 kilos, I believe. Let me see. Yeah, it's 50 kilos times our acceleration due to gravity is 10 meters per second squared. And so that means our force of gravity is 500 newtons, and our normal force is equal to that. So our normal force is 500 newtons. All right, Kevin pushes the 50 kilogram box with horizontal force of 60 newtons, but the box is not moved. What is the friction force? All right, let's see, if it's not moving, then, and you're applying a horizontal force of 60 newtons, then, and you're trying to move it in one direction, but the box isn't moving, then that box, or the plane, or rather the surfaces between the box and the table are exerting a friction force that's opposing you, that's equal but opposite, right? So if you're pushing with 60, that box is pushing back with 60, and that's a frictional force that's pushing back. All right, so 60 newtons there. All right, we're getting into Newton's third law now. Let's see. You bump into a heavy sumo wrestler. Again, you bump into the sumo wrestler. All right, sumo wrestler doesn't bump into you, or sumo wrestler is not moving, we're presuming. And it says here the sumo wrestler weighs 500 pounds, but this is a conceptual question. That doesn't matter. It's just saying it's a heavy person. Which force is larger, the force of the sumo wrestler onto you, or the force of you onto the sumo wrestler? Now, Newton's third law says forces are equal but opposite. When something or some object exerts a force on another object, when two things bump basically or collide, then the force that the object that it collides with exerts on it will be equal and opposite. All right. If I throw a ball against the wall, all right, let's assume as an ideal of scenarios possible and very little loss to friction. If I throw the ball at the wall and it bounces off, it will bounce off with more or less the same acceleration or speed coming off the wall as it did coming in. That means the force the wall exerts on the ball when it bounces off is equal, right? Now the wall's not moving, all right? So we can assume essentially the wall has infinite mass, okay? But as that mass starts to come down, those two things will interact, and then those forces will cause those two things to accelerate off of each other, all right? So in general, when something or one object, object one, interacts with or collides with a secondary object, all right, those two things have equal but opposite forces acting on one another, all right? This is not like the case up here when you have unbalanced forces. When you have unbalanced forces, this will cause objects to accelerate. We are talking about a scenario where one object is moving and bumps into another object, all right? And that will cause some interaction, but at that point where they collide, object one collides with object two. That means object two will provide an equal but opposite force applied to the colliding object. Okay, let's see here. And I think this is the exact same question, but just now a mosquito and a windshield. All right. A student is driving her car when an insect strikes her windshield. Which of the following statements best describes the force in this situation? The insect strikes the windshield with the same force as the windshield strikes the insect. Now, that's not to say that when the insect strikes the windshield and the insect will react the same from the collision. Of course not. They're going to react very differently from that collision, right? An insect hitting a windshield is going to explode, but they both experience equal but opposite forces. Now, a force is a mass times an acceleration. The insect, so let's say we have equal force, right? The insect has a very small mass. That means it's going to experience a very large acceleration. If you experience a very large change in acceleration, then bad things are going to happen, right? In this case, as an insect's case, it's going to explode, right? Now, a car, because it has a much bigger mass, is going to experience a very, very small change in acceleration. And so small that you don't even notice it when you're driving a car. You don't notice that change in acceleration when bugs hit your car, right? It is there, it is present. When a bug hits your car, it does cause your car to slow down, but it's so insignificant that you don't even feel it, right? But I tell you what, I bet you that insect feels it when it slams into the hood of your car, right? Bye-bye. Let's see here. I think this might be the last or second to last question. Earth pulls on the moon and holds the moon in its orbit. What is the equal and opposing force in this scenario? All right, the Earth is pulling on the moon, right? And the moon is pulling the Earth towards it. And you can think of it, these are balanced forces. Think of it like a tug of war match, right? The forces have to be equal in a stationary orbit like that in order for the two things not to move either closer or further apart, right? So the forces are equal, but opposite. And that's Newton's third law. Let's see here. So I think that more or less that actually covers all of the questions. I'm going to talk to the teacher that put this one up. She put the direction of the object's motion cannot be determined, but I'm thinking about this problem one way, and I'm going to talk to her about it and maybe see if there's something that I'm missing on this question. But I would interpret this as the force is being unbalanced, therefore it's going to cause an acceleration to the left. All right, especially given a frictionless surface, this should accelerate to the left. So I'll talk to her, but that basically concludes this session. There's really not a lot to it this week. I just wanted to go over the formative. We will have a formative next week, but it will be graded as a classwork. And then just go in the books only if it helps bolster or improve your grade. It's not meant to, trip you up in any way. All right, so that's the session. If you have any questions, please feel free to pop them up on the chat screen. Otherwise, you're good to go. I'm recording this now, and I will be posting this later so that you can rewatch or for others not in attendance to watch. All right, take care. I'll hang around for about 5 more minutes for questions if you have any. All right, have a good one. Why did I type that and say it at the same time? Sam, I'm still thinking about boats. That conversation we were having the other day. Yeah, I will. When I take my daughter out on the boat Friday, I'll take some pictures, and then when we talk next week, I'll share. The only issue is we are going fishing with what do you call them? Like those little dock rods that are like 3 feet long. So we'll see if I can catch a striper with a 3-foot rod. All right. Well, if you want the outboard, you can. We could talk more about that. Don't worry. Yeah, I definitely need to get rid of it. So it's just going to take up room in my garage, and I don't want it.